Okay, today we're going to talk about resilience. And in this talk of the resilience framework, we're going to begin by discussing what is resilience, how it's different than sustainability. And, often there's this statement, resilience is the new sustainability, but we'll talk about the kind of differences between them and then go back and frame a lot of this class in a resilience framework, and why I think indigenous resource management is a good example of a resilience framework put into action. So first, let's talk about sustainability. Like, what does sustainability mean to you? I'm going to give you an awkward pause and encourage you just to, when you think of sustainability, what's the top 3 or 4 things that come to mind? So often we see sustainability and hear sustainability around building practices, sustainably harvested. In fact, there's is it MRC? It's Marine Resources Council. Marine Stewardship? Oh, I'm blanking on it now. There's a group that puts out the seafood watch list about which in certifying fisheries as sustainable. That's a thing that you can get. You have to pay a lot of money for it, but it's a thing you can get within your fishery is certified as sustainable. Copper River salmon, Bristol Bay salmon, things like that. And so sustainability has this image, I think, of green, reusable, maintaining. I think it's often synonymous with having the same yield year after year, and it gets to be tricky when you define a sustainable economy and a sustainable ecosystem. And so one thing is, to have a sustainable economy, it has to have growth. It has to grow every year. A sustainable economy is growing at some rate, 2 or 3% a year. Well, is that achievable for natural resource extraction? Or are you going to get 2 to 3 times more, not 2 to 3 times, 2 to 3% more trees every year, 2 to 3% more fish every year? Arguably not. So that fundamentally, you're faced with a disconnect between sustainable fisheries from a biological standpoint, and then sustainable fisheries from an economy standpoint. That fundamentally there's a disconnect between the ecology and the economy right off the bat. And I think ecologically, when we think of sustainable, it's the avoidance of the depletion of natural resources in order to maintain ecological balance. Now, this is kind of a funny way of explaining it, but I think it's like a perfect fisheries example in some ways. So what this is it's a graph, simple XY, along the X, CPUE mussels per hour. CPUE is catch per unit effort. You got mussels, it's per person per hour. So what that means is, it's probably in kilograms. It's a French study. So it's saying 30 CPUE, which means normalized by effort, you could catch 30 kilograms of muscles per person per hour. Or if your CPUE is 180 per person per hour, you could catch 180 kilograms of muscles. So it's catch per unit effort. Catch here will be the number of muscles, and per hour, or I mean, sorry, per hour, person per hour. So one person 1 hour catches 30 muscles, one person 1 hour catches 180 muscles. Along the Y is density, muscles per square meter. So in a patch, meter by meter, how many muscles are there? From 0 to 30 muscles. So what this draws, there's a whole bunch of samples along this, and like I said, this is an estuary in France. What's really important here is this relationship. So if there's lots of muscles, you catch more per unit effort. If there are fewer muscles, you catch fewer per unit effort. The reason I bring this up is it draws this beautiful linear relationship. More critters, more catch, fewer critters, fewer catch. And so the assumption here is that, one, we can kind of, in theory, the fishery could regulate itself, meaning, if economically, if CPU hits 50 mussels, then it's not viable to go out, and so we'd never get below this density. Sort of like invisible hand sort of theory. But more importantly, given that there's a linear relationship between environmental abundance and catch per unit effort, we'd expect to move cleanly back and forth on this graph. So if there's a change in environmental abundance, there'll be a change in catch, and we can regulate and move back up to that change in environmental abundance. But what this is doing also is assuming that there's some staticness here, that this relationship maintains some level of stability, that there's not stochastic variables that are entered in here. There's not like episodic events that knock out mussel abundance, that there's not something that comes in and wipes out a lot of the mussels, or something that comes in and makes it relatively harder to harvest. That we're assuming this linear relationship between the two, and it's not encapsulating the ability for external perturbations to really alter the way that the system works. One way to think about that is in this comparison by Marchese et al. About the differences between sustainability and resilience. And here we've got time and then on the X and sustainability on the Y. And on our anti-resilient system, we're moving along, and then there's some perturbation that happens. A bunch of mussels die off due to a warming event. We're absorbing that problem. There's recovery and then adaptation after that, meaning we just adapt to a lower catch per unit effort. In a resilient system, we're moving along, and there's a disturbance. It bounces back more quickly. In this case, it's actually coming back to a higher pre-disturbance state. So sustainability, the measure of sustainability is relatively the same between these two systems, but the difference is resilience. One system, it has more resilience. It can bounce back from that change more quickly, where a system with the same level of sustainability is not able to adapt to that perturbation as well. So sustainability works until it doesn't. And the measure of from when it's not working to when it's back working can be thought of as resilience, right? So you can have two systems that are functioning the same, they seem sustainable, everything's great, and there's a big perturbation that comes in that takes a nice linear relationship and throws it on its side. And the ability to recover from that is resilience. And so really, when we're thinking about designing and managing projects and implementing restoration plans, we really need to build in resilience, the ability for systems to absorb and recover more quickly. This is the Swinomish Indigenous Health Indicator project that I'm a big fan of. And they talk about integrating change. It says sustainability. Culture isn't static, it adapts. E.g., people hunt with guns or use motorboats. That doesn't discount the significance of harvesting, but preserving the ability to move within homelands and voluntarily adopt changes in temporal or permanent, i.e. 7 generations of thinking. So this is under resilience to have the sustainability thought. I would argue that this is really looking at resilience, that the ability to adapt to changes is the definition of resilience, that just because we're using different tools and technologies than we did pre-contact, it doesn't make it less significant. And that's an example of resilience. And this article is talking about the end of sustainability, just a piece on realities of the Anthropocene, how environmental, climate change and the design of our systems are built around sustainability and not taking into account resilience. So we need to think about ways to keep our systems flexible and be sure we build in kind of those buffer zones, those places for nature to kind of run its course, that idea of resilient systems. Graphically, this is from Phil Lawrence, is kind of a good example of the idealized resilience. And here, we're going to look at it in 2-dimensional space, and then we'll look at it in 3-dimensional space as well. But in general, what we can think of is like a bunch of rolling hills, and then the system as a marble in those rolling hills. And so the system, in this case, it's not like the system like the man, it's the system like a Gary Oak ecosystem. And a Gary Oak ecosystem can be in between these 2 points in this trough, and you can bump it a bunch. You can have a fire. You can maybe introduce some non-native pests. You can introduce some logging. You can do a fair number of things, and it might push it up to the point or push it up to the top of the hill over here. But if it's a marble, it rolls back down. So it keeps rolling back and forth in this basin until you kick the system hard enough where the marble rolls from this basin up here and then into a new basin. And this can be thought of as here, the point being the tipping point, and then moving into the new basin is a new ecosystem state. So sticking with the Gary Oak example, here's a nice open Gary Oak ecosystem, big Gary Oaks, lots of grassland, lots of camas, and it's really resilient. It's experiencing light burns, it's experiencing a bunch of other impacts, but it's still trucking along as a Gary Oak ecosystem. Hits this point here and goes down into a new ecosystem state, perhaps by a reduction of light anthropogenic fires to maintain those open clearings. And now we hit a point where we have so many Doug firs that it tips to no longer being a Gary Oak ecosystem, but that same patch of ground now being a Doug fir dominated system. And it's here, and now it's resilient in the Doug fir system, and it would take a fair amount of effort to get it back over into the prior ecosystem state. So the idea is that we want systems that have high sides to this bowl, because that's a lot of resilience that can absorb big impacts, but that little ball or marble will always roll back down to the bottom. The gravity is pulling it down. And if we get up and over to a tipping point, then we wind up in a new ecosystem state, a new system state, and it's disproportionately harder to get it back than it was to get it there. We can look at that here in this example. Here's kind of the marble. This is more of a three-dimensional example, but you've got, your marble rolling around between one basin and potentially getting knocked over to the other basin, which would be the other ecosystem state. So these tipping points or bifurcation points. I like tipping points, kind of like a Malcolm Gladwell-esque, tipping point. And so here is attraction to certain areas. Once you're within this basin, you're going to be attracted back down to the bottom of it, and it takes a fair amount of energy to get up and over. And different, kind of like different persistent forces at work here. Okay, let's just talk about both of them. I thought I've got another one that I give an ecological example, but this is kind of a way of thinking about it. I often think of this as the I don't see them anymore, but there used to be these things you put a quarter in, and it was like a big funnel, and like the quarter goes down. I kind of think of it like that. Like if you're in the system, the resilience is going to keep you spinning around and around, and eventually go to the bottom. But then once you bump out, then your basin of attraction is down in here, and it's harder to get back out. To me, one of the classic examples of a tipping point are coral reef ecosystems. And so coral reefs are wonderful and beautiful and great, but they have a lot of resilience built into them. They have multiple grazers. They have a lot of redundant ecosystem services from different fish and invertebrates. But as we erode that resilience due to disease, die-offs, overfishing, eutrophication, they get to a point where they are no longer able to support coral, and they become an algal-dominated system. Algae overgrows all of the coral, corals die, and they become algae patches. So a lot of resilience in the coral reef systems, but as we, again, keep eroding and eroding and eroding, then they hit this tipping point where, one small thing happens and boom, we're in an algal-dominated system. It's like nearly impossible to go from an algal-dominated system back up the hill and back over to a coral-dominated system. So that level of energy that it takes to go from coral to algae is relatively little, where the level of energy to go from algae back to coral is a massive amount. And that's often the case with these thresholds and tipping points, is that basically it's easier to screw up than it is to fix. Breaking things is easier than fixing things. If nothing else, understand that. And some other examples of tipping points we talked about were the yellow cedar die-off. As we lose a few, then it kind of gets worse and worse and worse, and it's it would be hard then for these low wet patches, when all the cedars are dead, all the yellow cedars are dead, it'd be hard if one lands there. It's going to be pretty hard for that one to grow. It's going to be really hard to get that patch back once we lose it. And once it goes to an alternative ecosystem state, it's going to be hard to get back to a yellow cedar ecosystem state. Landscape scale management, burning, etc. Also very similar. Where it's been tried in the San Juans is Yellow Island. So Yellow Island's a small island owned by the Nature Conservancy, and they've done a lot of some burning and a lot of just straight on the ground, chainsaws and shovels to open up that landscape and create more of an open savanna-style landscape, which is contrasted to what most of the islands look like with these really densely packed forests. And here you can see camas and other wildflowers that bloom. Very different systems. Yellow Island is more of that kind of iconic Gary Oak, open landscape style savanna, and most of the islands are these densely packed forests. But they have to maintain that ecosystem state through a lot of active management, and unfortunately they're not allowed to just throw a couple matches out there and burn the place down. There's some houses that are, they have a house is a strong term. There's a cabin out there that the caretaker lives in. And they don't want to do a big burn because it would cause a lot of damage. So they have to maintain it through a lot of physical mechanisms. And if we bring that back into our attractor state, we could think of that again. It's like a Gary Oak ecosystem and a Doug fir dominated system that once you get into one of those basins, one of those ecosystem states, it's really hard to move to the next. We can add humans into the system, and so what's really popular is to talk about coupled human natural systems. And that's like science saying, oh wow, people are probably important in the system, so we should talk about coupled human natural systems. And one that I've talked about in my work in the past is thinking about clam gardens as the central to examine coupled human natural systems. And so we've got clam gardens, and we've got active clam garden management, which improves indigenous health indicators, connections of people and landscape. That's related to the human system, which is increasing cultural sustainability. Maybe resilience is a better word to use there, which then increases people's wanting to participate in clam garden management and restoration. So this is today, as we restore clam gardens, people have value in participating in that clam garden management. It helps strengthen identity and connection to place, and it helps drive more participation in clam garden restoration. On that natural system, active clam garden management alters physical and biogeochemical properties, which increases ecological sustainability, and that improves clam recruitment and biodiversity. So there's increased benefit there, and I should probably use resilience instead of sustainability in both of these, because that's really what I'm talking about. And this is work I did a while ago, so maybe it's not in the resilience framework. But by having both of those, you're both benefiting people and you're benefiting the environment. Active management of clam gardens increases ecological benefit. It's more clams, happier clams, more critters in the rock wall. Having people engage in the ecosystem strengthens identity, connection to place, exercising inherent rights, strengthens cultural connections, strengthens family connections. All of those things are happening through an integrated coupled human natural system. Here's the one I was looking at. So if we go here, where if left to its own devices, nature would make Doug fir monocultures, but social power, i.e. indigenous resource management via burning and indigenous people's desire for ecosystems that have certain things, camas, open prairie lands for grass, open lands for movement, berries, other traditional foods. Human desire pushed the ball from the Doug fir basin into the Gary Oak basin. If left without human intervention, the systems would be Doug fir dominated. Human intervention is keeping the ball in the Gary Oak, or was keeping the ball in the Gary Oak basin. Loss of that traditional management then allowed the ball to hop out of the Gary Oak basin into the Doug fir basin. So societal pressure kept Gary Oak ecosystems alive and thriving. Now that we've lost societal pressure for that, we're seeing Doug fir dominated systems. Clam gardens I just talked a bit about. Additionally, there's the idea of sustainability for like clam harvest, getting the same amount of clams every year. But then there's the thoughts of resilience, of adaptation to sea level rise, having a system of these. So if clams were bad at your one beach, you've got another beach somewhere else that you might not maintain but have familial connections to and are able to harvest there. So it allows for variation in productivity. There's a system of governance around it, that some are shared, some are owned by individuals. It's a source of starvation food, so when other food sources are in peril, clams are always there to save the day, and it increases the availability of clams. And so from a sustainability standpoint, we're just thinking about like number of clams, but from a resilience standpoint, you're thinking about the connections between and within, and how they can help support people when other foods are failing. I think reef nets also tell a cool story that's very similar in many ways. And so with reef nets, remember that there's a whole bunch of things going on, and they have to happen correctly to get a fish in the net. You got to come together, you got to build the net, you got to put it out, you got to put it out exactly where it needs to be, you need to follow all these protocols, you need to fish on a certain tides with it facing a certain way, and the fish have to swim into your net. No matter how hard you try, you can't make the fish show up. And I think that's a really interesting aspect of resilience, in that if your reef net is over here off the south end of Lopez, and fish don't happen to go that way, if they happen to go around the west side of Lopez instead of the south end, you're not going to catch very many fish. So you're going to have to use a familial connection to access fish on the other side of the island. It's entirely dependent on fish behavior, and fish don't behave like we want them to. And so it helps reaffirm those familial ties. It also reaffirms social standing. Who's the reef net owner? Who's the crew? Like, what shares do you get? That kind of thing. And Coast Salish agriculture in the broadest sense, in the sort of Matthews and Turner sense, where we're looking at the land and the seascape as a complex intertwined system, where if environmental conditions are bad for one or two types of foods or one or two types of systems, you have other types of systems that would do well in those conditions. And so we're not banking it all on one suite of parameters, that there's a lot of resilience built in, there's a lot of variability built in, as well as the ability to adapt to sea level changes by moving rock systems up and down the beach, relying on multiple different species and not fully utilizing all of them all of the time, keeping some in reserve, so when other things fail, like fish populations will fail due to natural environmental variability, you have other backups on hand, clams, etc. And this aspect of burning and camas, I think, is really important as well, that we're thinking about what is the relationship between ecology and societal impacts, sort of the restoration ecology versus restoration science sort of aspects, that we're really shaping ecology to socially desirable landscapes, and how people can use those socially desirable landscapes to increase food productivity and diversity, allowing multiple pathways to build a resilient direction, meaning not putting all of the eggs in one basket, if you will. And so camas is one example of that, where you've got multiple gardens that are rotated through, that are tended by different families, but really kind of zooming back out to the whole like Coast Salish ag idea of multiple pathways, multiple systems of food production and management that I think don't all follow the same pattern or the same beat. Which is not to say if you have a 20-year drought, things aren't going to be bad, which is to say that not everything is tied up within one specific area or one specific type of productivity. Not everything is tied up in like wheat and corn, right? Like it's a fair amount more diverse. So it's an interesting way to think about ecology and an interesting way to think about what our sort of societal outcomes are. And this paper that Anne and others wrote is really quite great. And so I encourage you to kind of think about that critically. And hers is really like thinking about practice, like putting it into practice. How do we engage people in the practice of conservation and resilience, and how do we train students within that framework? So Haishka, thank you.